Video number 8, convex mirrors again. Example number 2. Still studying light, still studying mirrors here at BHS, the Harvard of the MVL. All right, so what we're going to do is we're going to take our paper, turn it on its side, draw in our x-axes. Easy enough. Okay, there's my x-axis. Let's put in my y-axis. This time around, we are going to be looking at what happens when an object is placed pretty close to the convex mirror. Now, what's nice about convex mirrors is that the application of our ray rules, how we come in and how we leave, it doesn't really change. That's the good news. So in this example, I'm going to place an object. Remember, this is negative and this is positive sides of the mirror. I'm placing an object 1, 2, 3 away, object 3 tall, and the focal's over here 1, 2, 3, 4, 5 for -5. And there we have our setup. Now what we're going to do is we're going to use our graph, and we're going to try to come up with DI, HI, and magnification. So no different than what we did last time. We use our ray rules. So you might recall the ray rules are: you come in parallel, you leave based on the focal. You come in based on the focal, you leave parallel, and you go through the origin and you leave at equal angle. Remember, it's still a mirror, so it still bounces off. It's just the way that it bounces off when you come in parallel is based on the focal. We never actually travel through the focal. Remember, it's virtual. You can't go through a virtual focal. All right, we try to get to the virtual focal, but before we can get there, we hit the reflective surface, and the way we come off is parallel to the X. So that's my second ray. Notice they're never going to intersect, so that's why this is going to be virtual. Only flat part of this curved mirror is the origin. We hit the origin and then we leave at an equal angle. We can accomplish that by counting down 3. So at the point +3, -3 for height is how we will leave. Now we're going to trace back these lines. Trace it on back. Trace it on back. Trace it on back. Running out of noises. All right, so where these things intersect is where the image is going to form. So here's my image. I for image. So if we look into this convex mirror, it's going to look like a lot smaller, but it's still going to be upright, and we won't be able to project it. So that's a virtual, reduced, erect kind of image. Let's count. Love counting. So I'm going to come over, I'm going to round it up because, I don't really feel like messing with decimals. -2. Height. 2. Probably a little bit less. Magnification. Well, that's easy. We'll take this 2 and compare it to this 3. So what would that be? 2/3, which is times 0.667. Watch out. Okay, so now we're ready to do our math and see how close we get to these numbers that we just calculated. Math. First thing we're going to do, I'm going to turn my paper. Oh, yeah. So we're going to do 1/f equals 1/di plus 1/do. Lensmaker's equation. Remember, illegal, can't use pink, only use the givens. So we have 1/3 plus di is what we're solving for, so we'll just leave that di. And then the focal length, -5 because it was convex. I've been using 5. On the problem set, you'll use 8. Then what we got to do is find a common denominator. 15, right? So we're going to get 1/-15 is equal to 1/di plus 5. Whoops. I meant to say -3/15. Over here, I would get 5/15. So then we'd subtract 5/15. In other words, we're going to make this into a bigger negative number and get -8/15, which is equal to 1 over di. Then flip it, and we're going to get -15/8. What is that? Time to ask the calculator. So I'm going to say -15 divided by 8. What do we got? -1.875. Now you know I rounded to 2. Okay, so that is the exact answer. We will call that our math answer. Let's compare that to our previous graph answer. -1.875. I said 2. Not too bad. I've been getting better and better. Yes. Okay, so now we got to do magnification stuff. Remember, magnification equals HI over HO. It also equals -DI over DO. So what do we do in this example? Well, we can only use our givens and things that we solved for in the math. So that means we're going to start with U. Negative of a negative is a positive. So that makes that like positive 1.875. And then for the bottom, we're going to put in the distance to the object 3. That's going to give me my magnification. So I'm going to hit second answer on my calculator. And then I'm going to divide by 3. -0.625. -0.625. So magnification, which is expressed as a multiplier, times -0.62, should be positive. Definitely positive. Positive 0.625. Okay, so now we can use that magnification 0.625 and we can set that equal to HI over HO, where HO is another given. It's 3. So I'm going to take 3 times 0.625 and I'm going to get my height of my image, 1.875. Let's go ahead and we'll put that in. I guessed 2 from my graph. So we get some agreement. Now, just like last time, when it comes time to describe this image, the way we will describe this image is virtual. How do I know it's virtual? It's on the negative side of the mirror. The rays never intersect. It's pointing up. It's erect. And it's smaller than it started, so it's reduced. Looking at the numbers, you can tell the same stuff. Negative sign is virtual. The fact that it's greater than or smaller than the original object height of 3, you're like, okay, it's reduced. And you can also tell it's reduced because it's less than 1. And it's erect because the sign of the magnification is positive and the sign of the image is positive. The end. We have mastered mirrors. Now all that is left for you to do is to finish that problem set. Remember, on the problem set, you get more than one submission. So you can plug it in and see how you do, and if you have any errors, you can do it again. Remember, you got to give me time to grade the graphs, though. It's due at 11:59 on Friday night. That was by popular request, as I asked you in the emails. All right, 9 minutes, not too bad, not too shabby. See you.